Everybody, Physics Ninja here. Today we're going to look at calculating the position of the center of mass for this semicircle. It has a radius r, and basically we're just going to apply our formula for a continuous object. Right, what we have is a semicircle, which is just a 2D shape, and the mass is uniformly distributed over that complete area right here. So what we're going to do here is first take a guess where the position is. Right? Imagine if I had a rectangle. If I had a rectangle that had a width equal to r, it would look something like this. So it's kind of a poorly drawn rectangle, but I just want to highlight an important point. If this was a rectangle and I was asked, I wouldn't even do any calculation whatsoever, right? I would simply go, well, it's got to be right at the middle. If the mass is uniformly distributed, this would be the y position of the center of mass, and the x position would simply be 0, right? It would be on the axis here, right in the middle of that rectangle. Now in this case here we have a semicircle. So basically what we've done is we've taken a rectangle and I've removed some of these corners over here, right? I've made it into a circular shape. So by removing some of the mass, what I'm doing now is I would expect at the end, when I'm done all my calculus, that I should obtain a value that is less than r over 2. Because if it's a rectangle, this position here should be r over 2. Right, so in this case, let's go ahead and do it now. Let's apply our calculus and calculate what the position of the center of mass is. So what I'm going to do here is I'm going to solve this problem using 3 different methods. They're basically equivalent to each other, but I think it's kind of nice just to see different things when you're first doing these types of problems. The first one here, what I'm going to do here is I'm going to break this down into a whole bunch of tiny little masses here. We're going to call these dm's. And again, our equations are for the x center of mass, it's a integration of x, adding all of these masses together and divided by basically the total mass down here in the denominator. And for the y position of the center of mass, it's a simple equation, right? It's similar, you just swap the x for the y and that's it. The one thing we should notice for this, since it is symmetric, we should obtain at the end of the day that the x center of mass should be 0 when we plug our information into this equation. Now again, what I'm assuming here is that the mass density is a constant value. So it doesn't matter where you look. If the little area is the same, the mass inside that little area is going to be the same, right? And this mass density is simply the total mass of the object divided by the total area. Now again, I'm dealing with a half circle, so this equation applies, except y is only positive value, right? If it was a full circle, then y could take on negative values, but in this case, strictly positive. So method 1, just slicing it up into little squares and adding them all up and doing this integral for both x and y. In method 2, what people often do here is, they break this down into either vertical stripes, right? And then you simply add up all of my vertical stripes. So each of these vertical stripes, it's going to have its center of mass located right at its center. So notice that the vertical stripes that are at the end, they have a center of mass that's a little bit lower. And the ones that are closer to the center have their y position of the center of mass a little bit higher. So that's one way of doing it. Another way of doing it here is to break this down into slices that are horizontal instead of vertical. Now each one of these now has its center of mass kind of at its center again. So that one would be there. If I take a vertical slice kind of near the top of the circle, it looks like this. And again, its position of the center of mass is right up here. So anyway, we're going to highlight this using the 3 different methods, just so you get an idea on how to solve the problem. So here's method 1. Again, method 1, I'm just going to break it down into a whole bunch of small masses like this. And they are going to be a certain distance, little r away, and this makes some angle theta, say, with respect to the x-axis. So that means that its value of x here would simply be, write that in cylindrical coordinates, right? We have r cos of theta, and the y value here, the vertical, is simply going to be y, and that's r sine theta. All right, let's first focus on the denominator. That's the same for both cases. Again, we have a constant mass density. So again, that's simply the total mass, right? The total mass is you simply integrate over the area and you add up all the mass. So in this case, it's very, very simple, right? It's going to be my density multiplied by the total area of this half circle, which is simply pi r squared and over 2. All right, so that's the total mass. That's the term that's going to go in the denominator. Now again, my sigma is mass over area. It's also dm over the little bit of area in this little patch over here. Call that dA. Right, this is constant. So what we're going to do now is first look at the x position, and the x position is pretty straightforward. All you have to do now is you have to integrate, and we're going to make a change here. We're going to go into cylindrical coordinates, and that makes sense for this problem, right? Just because of the symmetry of the problem. So our x value becomes what? The x value is what I wrote over here. It's r cos theta. Let's go ahead and substitute that. And dm now, dm is over here. It's simply going to be my density multiplied by that little bit of area over here. So this guy here becomes this constant mass density multiplied by the area of this little patch. And again, all that now gets divided by our total mass, which is what I evaluated here. So this is sigma pi r squared and divided by 2. So one thing we notice is that if the sigma is constant, which it is in this case, it actually cancels out. So that's going to be important. So now all we have to do is substitute in what this little bit of area is. And we're dealing in cylindrical coordinates here. So the area, or that little bit of area, again, I'm going to be integrating from 0 all the way to the radius of the semicircle. And the angle now, the angle gets integrated from 0 all the way to pi. Not all the way to 2 pi, because I'm only going 0 to pi in this case. So again, we still have r cos theta. And now dA, again, in cylindrical coordinates, this becomes r multiplied by d theta dr. Okay, and again, we have to divide here by this factor here, which is simply half the area, pi r squared over 2. Okay, we can simplify this a little bit. Group both of these r's, that becomes r squared, and then all you have to do is evaluate this integral over here. And again, this was the x center of mass. So let's go ahead and do this. X center of mass. Let's go ahead and write this term, pi r squared over 2. And now, again, we're going to write down the integral here from 0 to r, 0 to pi. And this here becomes r squared dr. And the next term here becomes cos of theta d theta. All right, so this is what we have to evaluate for the x position of the center of mass. Let's go on the next page and finish this up. All right, so this case here is actually pretty straightforward because of this function right here. Right? If you remember what the graph of cos looks like, let's go ahead and just sketch it out here. And this is the angle theta, and this is what cos looks like. Right? This is cos of theta versus theta. It starts at 1. Then it goes to 0 at 90 degrees, or at pi over 2. And then it goes all the way to minus 1 down here, right? And this is right here at the angle of 180 degrees, or the angle pi radians. All right, and then it eventually goes back up. But actually, this first integral right here, this guy combined with the cos theta over here, I'm only integrating the cos up to here. And that means that all I'm doing here is I'm simply adding this area to this area right here. But this area over here has to cancel this one over here. Now either you can actually do the integral if you know that, but just by looking at the sketch, you can automatically see that the integral from 0 to pi of cos theta d theta has to be equal to 0. Okay, and that one was pretty straightforward. So the x position of the center of mass has to be 0, and that's clearly evident because of the symmetry of this problem. So all we have to do now is find where is the y position of the center of mass. Right? It has to be on the x equals to 0 position. Go back now and look at our y center of mass. Again, it's divided by the total mass, so that term here doesn't change. Let's go ahead and make a big line. All right, so here we still have sigma pi r squared over 2. And now the top here is, now we can go a little bit faster since we've done this before. It looks very, very similar to the x. So I'm going to be integrating from 0 to the total radius. And I'm integrating from 0 to pi for the angle. And now I substitute what the y value is. The y value in this case was r sine of the angle theta. And now the dm again was our mass density multiplied by the little elemental area, which again was r dr, d theta for cylindrical coordinates. And that's it. Now again, we can proceed as we did before. We have constant terms that you could take out of the integral. And what you're left with here is just a nice integral here from 0 to r. If I group together all the r terms, I simply have r squared dr. And I can bring out the angle terms. And this is sine theta, d theta. And all of that has to be divided by, I'm just going to write it over here, as pi r squared over 2. Okay, and that's the y position of the center of mass. So we can do each one of these independently here. What you're doing here, this one is pretty easy. This simply becomes r cubed over 3 for this first term. And that gets multiplied by the integral of sine theta d theta. The integral of sine theta is cos of theta. And again, that's evaluated between 0 and pi. And all that has to, at the end of the day, we have to divide by this term over here, which is half the area. Okay, so be a little bit careful here. We have terms everywhere. But let's evaluate first this guy here. So we have negative cos of pi. That gives me negative and another minus 1. So that becomes a 1. And then minus 0 on this guy here at the end of the day. Just make sure you get 2 for that value. Okay? Now we group it all together. So what are we left with? We can cancel out a couple of these radius. We have radius squared in the denominator. We have a cube here, so we can get rid of 2 of those. And that's it. Now we put it all together, and what you end up getting here is the y position of the center of mass. All right, so we have r, and we have over 3. That one doesn't do anything. What about these guys over here? This still becomes 2. And here I was dividing by 1/2, and it happens again, and there's a pi factor in there. Oh, pi should be in the denominator. And then the other half actually gets brought to the top. So what you end up getting at the end is 4r divided by 3 pi. All right, if you're a little bit careful with the math, this is what you should get at the end of the day. Now, if you have a look at what this looks like over here, imagine pi was simply equal to 3, so it's kind of like 4 over 9 multiplied by r, which is a little bit less than half, right? If I go to half r is there, a little bit less than half would be right over here, right? This is roughly 4r divided by 3 pi. All right, and there you have it, folks. This is kind of what we'd expect just from the beginning from our simple approximation, comparing it to the rectangle. All right, so this is method 2 here. Method 2 is we're going to break this down into vertical slices. And again, we're not really going to worry about the x center of mass. We know that that value is 0, so let's just focus on the y value when we break it down into slices like this. So I'm going to look at one of these slices over here. The little mass of each slice over here is going to be our mass density and multiplied by the area. And actually, if I take this one step further, what is the area of this little slice over here? Now, the area of the slice would be, what is the height? The height is, again, they're all simple rectangles, right? So the height is simply y, which extends all the way out here. And then the thickness is simply going to be dx, right? How thick is that slice is dx. So now we have to go ahead and substitute things in our equation over here. The denominator is the exact same as before. That hasn't changed because I'm adding up all these slices, and at the end it's simply the total mass of this semicircle. All right, so it's just the numerator here that changes. And again, here I have to add up. Now, what is the y value here for each slice? Well, the y value is, what is the value of the center of mass of each one of these slices? So you have to think about this for a minute. This is actually going to be y over 2 if I'm breaking it down like this, right? Each one of these, it's not going to be the value y, is I'm adding up the center of mass of each one of these tiny little slices. So this guy here actually ends up being the center of mass of each slice, which is y over 2. Okay. The element of mass is given by this expression over here, which is my mass density, and multiplied by y, multiplied by dx. And all that gets divided by my total mass, which is same as before, pi r squared divided by 2. Now notice we have these factors of 2 those cancel out over here. And the limits of integration over here simply go from, well, as they span all of the x values. The x values can go all the way from minus r all the way to positive r. Now the other thing I can cancel again is the sigma. This here does not matter. All right, let's clean this up a little bit and we're going to see what we're left with. So the y position of the center of mass, again, I'm integrating from minus r to r. And this here becomes y squared dx. And again, all of this gets divided by pi r squared. Okay, so let's think about this top part over here. Again, y values, now what I can do is I can use my equation for my circle. Y squared simply equals to r squared minus x squared. All right, so I have to make this change a variable here because y depends on x. So let's go ahead and substitute that in there. And y squared I can write as r squared minus x squared and integrated over dx pi r squared. Now this is an even function over here. What you can do is actually, instead of integrating from minus r to r, what you can do is simply integrate from 0 to r and multiply by 2. All right, that's kind of a simplification we can make. That makes our life a little bit easier. And let's go ahead and evaluate this now. I'm going to take out the denominator term. This is simply pi r squared. Put that to the front. And now I'm left with the integral. Oh, I still have the factor of 2 there. That's a constant term. Can take that out. And now this first term here simply becomes r squared x. Again, 0 to r and minus. This becomes x cubed over 3 and 0 to r. All right, when you put the zeros in there, you never have to worry about those terms. So all we're really left with here at the end, running out of space here. Let's take that to the next page and evaluate the rest of this expression over here. Okay, so I'm going to simplify this. This is pi r squared. After you substitute values of r here, you get r cubed and minus r cubed over 3. So what are we left with here? This term here in the bracket, you can simplify that guy. All right, this is simply 3r cubed over 3 and minus 1. That becomes 2r cubed over 3. And look what we get at the end. You can cancel out r squared with 2 of those and multiply through. And my final expression here for the y center of mass becomes 4r over 3 pi, same as what I previously had using the cylindrical coordinates. All right, let's show you the last method now, where I'm going to break it down into horizontal slices. The last method now, we're going to break it down into horizontal slices. Now remember, when we use our equation here, the y now becomes really the center of mass of each one of our little units, each one of our slices. Okay, so this is really the center of mass of each slice. Okay, so almost done. Y center of mass. Again, this denominator is always the same. It's going to be the mass density multiplied by the total area, which is simply 1/2 pi r squared. All right, what's the top now? So the top, again, if I break it down, so each one of these slices now has a thickness delta y, and its width, I want to calculate what the area is, really, because what I'm doing here is I'm evaluating the position. The height of each one of these slices is simply going to be given by y, so that term doesn't change. Now the mass of each one of these slices is going to be the mass density and multiplied by the area of each slice. Following me up until now? Okay, good. Here we're going to have y sigma. Now what is this area, right? The area dA has to simply be equal to 2x and multiplied by dy. That's the thickness or the height of this rectangle over here. And the 2 simply accounts for the fact that I'm going from one end all the way to the other end. So let's go ahead and substitute that right here. So this here becomes 2x dy and divided by 0, 1/2 pi r squared. Simplify those sigmas. Those are constant terms. They don't play into this equation over here. I can combine these twos, this 2 with divided by half. That gives me a factor of 4 here. So I'm left with 4 pi r squared. And again, now I'm going to be evaluating this term. This integral goes, I'm multiplying x with y. That seems a little bit strange. And also multiplied by dy. And really I'm integrating y, should go all the way from 0 all the way to r. Okay, and that's it. Now we're just about done. The only thing you have to do now is evaluate this integral, which is not quite as obvious as the previous cases, but it certainly can be done. Okay, so what I'm going to do now is I'm going to simply substitute in, get rid of x. Since x is also a function of y, by using my equation up here. So we can write this out here as 4 divided by pi r squared. Integrate from 0 to r. Now the x value, again, if you isolate x over here, what you end up getting is a square root. And this becomes r squared minus y squared. And all that is multiplied by y dy. So you're left with this nasty looking integral over here. However, this is actually not that hard to evaluate. I'll show you how to do that in just the next slide. We're just going to use a substitution for the term here under the square root, and that actually ends up simplifying the problem quite a bit. To evaluate this integral here, what we're going to do is we're going to do a change of variable here. I'm going to call kind of u squared. Let's just do this. U squared equals the term up here. So this here will simply become the integral of u. And what we have to do now is you have to replace this factor over here. But by making this change of variable here, it becomes very, very simple. If you differentiate both sides of this, what do you end up getting? You get du. Sorry, 2 times u multiplied by du. If you differentiate a constant term, you get 0. And here you get minus 2y dy. You can get rid of those 2's. Anyway, you can see that this second factor here is exactly the one that appears right here, which is kind of nice. It makes that change of variable pretty straightforward. The other thing you have to worry about is the limits of integrations. So for example, when y equals to 0, u is equal to r. And when y was equal to r, u is equal to 0 in this case. So we do end up kind of switching the limits, but this is what it looks like. Have no fear. So actually we're going to be integrating now. It's kind of backwards, right? We're integrating r to 0. All right, this term over here is simply u. That's the definition of u, right? If you take the square root on both sides, this is what you get. And this other term here we just said was going to be minus u du. Okay, so take that negative sign, put it out to the front, and you're left with a very, very simple integral. So this becomes minus 4 pi r squared. And the integral backwards here of u squared du. Okay, so the last step over here, let me give myself plenty of room. If you wanted to, you could absorb this negative sign by, again, just switching those limits again. Maybe that's what I'll do. I'll just keep it like this. And you can kind of see where this is going. So just swap the negative sign, change the limits of the integral again, and you're left with this. And you've seen this guy before. This guy here is simply u cubed divided by 3 and evaluated between both of those limits over here. So you get 4 pi r squared and multiplied by r cubed over 3. I can cancel out 2 of those. That eliminates this term. And we're left with the same answer now. If you've done all 3 cases, you will never forget this. All right, here we have, that's our position of the y center of mass for the semicircle. All right, so a little bit below over there. All right, I think I've killed this problem to death here. Hope you enjoyed the video. Thanks for watching.